Look at any photograph of the night sky taken by a powerful telescope. Galaxies appear everywhere. Spirals, ellipticals, irregular clouds of light scattered across the darkness like glowing islands in a cosmic sea. They look close together. They look like neighbours separated by manageable distances. That impression is one of the most dangerous lies in all of astronomy. The actual distance between galaxies is so enormous, so overwhelmingly empty, that it turns the universe into something far lonelier than any photograph suggests. Even our nearest large galactic neighbour sits so far away that light itself needs 2.5 million years just to cross the gap, and between those galaxies lies almost nothing. A void so vast and so utterly barren that it redefines what the word isolation means. If you want to see why the space between galaxies is the most terrifying distance in the universe, do me a favour and consider tapping that like and subscribe button. It genuinely helps this channel keep making these deep dives, and I really appreciate every single one of you who sticks around. Now, settle in, get yourself comfortable, let's begin. Open any astronomy book published in the last 30 years. Find the photographs taken by space telescopes pointed at the deepest reaches of the cosmos. You will see galaxies everywhere. Thousands of them packed into a single frame, spirals tilted at elegant angles, ellipticals glowing like golden lanterns, irregular smudges of light scattered between larger structures like cosmic confetti. The images are breathtaking. They are also profoundly misleading. When you look at a deep field photograph from the Hubble Space Telescope or the James Webb Space Telescope, your brain does something automatic and dangerous. It treats the image as a kind of landscape. It sees galaxies positioned near each other on a flat plane and assumes they are neighbours. The way houses sit across a street, the way boats float in a harbour. Your mind fills in the gaps with an assumption of proximity because that is what your visual system was built to do. Millions of years of evolution on the African savanna trained your brain to judge distances based on how objects appear relative to one another. Something that looks close must be close. Something positioned next to another object must be nearby. This instinct serves you well on Earth. It will betray you catastrophically when applied to the universe. Those galaxies you see clustered together in telescope images are not clustered at all. They are separated by distances so enormous that the word distance barely applies. Many of them sit millions of light years apart. Some are separated by tens of millions, others by hundreds of millions. A few are billions of light years from their apparent neighbours in the frame. The photograph compresses all of this depth into a flat image, and your brain does the rest, collapsing inconceivable gulfs into the cosy illusion of a crowded room. Consider the Hubble Ultra Deep Field, one of the most famous astronomical images ever taken. Astronomers pointed the telescope at a tiny patch of sky, a patch so small you could cover it with a grain of sand held at arm's length, and kept the shutter open for 11 days. The resulting image revealed over 10,000 galaxies in that single minuscule sliver of sky. 10,000 galaxies crammed into a frame smaller than a fingernail held against the night. Your eye sees density. Your brain sees neighbours. But many of those galaxies are separated by billions of light years of empty space. Some existed when the universe was less than 1 billion years old. Others are relatively nearby, only a few 100 million light years distant. The image flattens all of this cosmic depth into a mosaic that looks like a crowded jewel box, and the lie becomes almost irresistible. You would never guess, looking at that image, that the dominant feature of the universe it depicts is not the galaxies but the emptiness between them. This is not a minor misunderstanding. This is the single most dangerous optical lie in all of astronomy. It makes you believe the universe is full in a way that implies connection. It makes you feel that galaxies are scattered like stars across a sky, separated by manageable distances, reachable in principle if not in practice. The truth is the opposite. Galaxies are among the most isolated structures in existence. The voids between them are so vast and so empty that even neighbouring galaxies exist in a kind of cosmic solitary confinement. And the scale of that separation is something most people never confront, because every image they have ever seen was designed, unintentionally, to hide it. To understand why intergalactic distances are so terrifying, you first need to understand what a galaxy actually is, not as a word, not as a glowing shape in a photograph, but as a physical object with a real size that already exceeds anything the human mind can comfortably hold. Our galaxy, the Milky Way, is a barred spiral containing somewhere between 200 billion and 400 billion stars. Current estimates lean toward the higher end of that range. Each of those stars is a thermonuclear furnace, many of them orbited by planets, moons, asteroids, and comets. The entire structure spans roughly 100,000 to 200,000 light-years from edge to edge, depending on how you define the boundary. Some measurements that include the faint outer stellar halo and the dark matter envelope push that number even higher. For the purposes of understanding intergalactic distance, even the conservative figure is staggering enough. 100,000 light-years means that a beam of light, travelling at 186,000 miles per second, the fastest speed permitted by the laws of physics, you would need 100,000 years to cross from one side of our galaxy to the other. That single fact should stop you cold. Light is not slow. It crosses the distance from the Earth to the Moon in about 1¼ seconds. It reaches the Sun in roughly 8 minutes. It passes the orbit of Neptune in about 4 hours. It passes the orbit of Pluto in about 5½ hours. Yet this same light, moving at the absolute cosmic speed limit, would need 100,000 years to traverse the structure you live inside. When the light now arriving from the far edge of the Milky Way began its journey, modern humans had not yet left Africa. Entire civilizations have risen and fallen in the time it takes a single photon to cross our galactic home. The Milky Way is so large that the speed of light, the fastest thing in the entire universe, is too slow to cross it in anything resembling a human lifetime. It is too slow to cross it in 1,000 human lifetimes. It would need roughly 1,300 human lifetimes, end to end, just to make the trip. This is the scale of a single galaxy, one structure, one island of stars. And you need to hold this scale firmly in your mind, because it is the ruler against which intergalactic distances must be measured. Whatever number you are about to hear for the gap between galaxies, remember that the galaxy itself is already absurdly, incomprehensibly large. The distance between galaxies is not measured in miles or even in light years the way we measure planetary or stellar distances. It is measured in multiples of galaxy lengths. And when you realize how large a single galaxy length already is, the multiples become devastating. Now look up on a clear autumn night from the northern hemisphere. Find the constellation Andromeda. Locate the faint, hazy smudge of light that sits just off the chain of stars marking the constellation boundary. That smudge is the Andromeda Galaxy. It is the most distant object visible to the unaided human eye. It appears small, it appears faint, it appears manageable. It is none of these things. The Andromeda Galaxy is a monster. It contains approximately 1 trillion stars. Its disk stretches across roughly 200,000 to 260,000 light-years, making it comparable in size to our own Milky Way, and possibly somewhat larger. In January of 2025, NASA released a stunning mosaic of Andromeda, assembled from over 600 overlapping Hubble Space Telescope observations taken across a decade of work. That mosaic resolved approximately 200 million individual stars, and it still captured only a fraction of the galaxy's total stellar population. Andromeda is a gravitational empire containing thousands of star clusters, billions of planetary systems, and a supermassive black hole at its center, with a mass exceeding 100 million times that of our Sun. It is not a small neighbor, it is a full-scale galactic civilization sitting across the void from us, and it is approximately 2.5 million light-years away. Say that number slowly. 2.5 million light-years. Let your mind try to process what that means in physical terms. A light-year is roughly 6 trillion miles. Multiply 6 trillion by 2.5 million, and you arrive at a distance of approximately 15 quintillion miles. That number has so many zeros it stops being a number and becomes an abstraction. So let me bring it closer to something you can feel. The Parker Solar Probe, which in December of 2024 became the fastest human-made object in history, reached a speed of approximately 430,000 miles per hour as it swung past the Sun. At that speed, you could travel from New York to Tokyo in under a minute. You could circle the entire Earth in about 3.5 minutes. This is the pinnacle of human velocity, the absolute fastest any machine built by our species has ever moved. At the speed of the Parker Solar Probe, the journey to the Andromeda Galaxy would take approximately 4 billion years. Not 4,000, not 4 million, 4 billion. That is roughly the current age of the Earth. You would need to travel at the fastest speed humanity has ever achieved, without stopping, without slowing, for a duration equal to the entire geological history of our planet, just to cross the gap between two galaxies that astronomers describe as neighbours. Even light, the ultimate cosmic messenger, needs 2.5 million years. If you could somehow freeze the Andromeda Galaxy in time and fire a laser beam at it right now, the photons would not arrive until 2.5 million years from now. By the time that signal reached the other side, whatever civilization sent it would almost certainly be unrecognizable or extinct. The gap is not just far, it is temporally ruinous. It destroys any hope of timely communication, let alone physical travel. And here is the part that truly breaks intuition. Andromeda is close. By galactic standards, it is practically next door. It is the nearest large spiral galaxy to our own. When astronomers talk about nearby galaxies, Andromeda is the first name they mention. It is our most immediate peer, our closest gravitational partner, the galaxy most likely to interact with us in the future. In roughly 5 to 7 billion years, Andromeda and the Milky Way are expected to collide and merge into a single massive elliptical galaxy, though recent studies place the probability at somewhere between 50 and 90%, depending on the gravitational influence of other local group members. They are already approaching each other at approximately 250,000 miles per hour. This is not a distant hypothetical. It is a confirmed trajectory, measured through decades of spectroscopic observation. Two galactic empires, each spanning hundreds of thousands of light years, each containing hundreds of billions of stars, are locked in a slow gravitational embrace that has been tightening for billions of years. And the gap between them is still so enormous that their approach speed, impressive as it sounds, barely registers against the distance remaining. Yet even this galaxy, this neighbour, this partner, on a confirmed collision course with our own home, sits so far away that light needs 2.5 million years to bridge the distance. The photons entering your eye when you look at that faint smudge in the autumn sky left Andromeda's stars before the genus Homo existed on Earth. You are not seeing a galaxy as it is now. You are seeing a ghost, an image frozen in deep time, delivered across a void so wide that the entire history of human evolution fits comfortably inside the transit. Every step our ancestors took out of Africa, every language they invented, every empire they built and lost, every war they fought, every scientific revolution they sparked. All of it happened while those photons were still in transit, still crossing the emptiness between here and there. And Andromeda is just one member of our local galactic family. The Milky Way belongs to a gravitational association called the Local Group, a collection of galaxies bound together by their mutual gravitational attraction. As of the most recent surveys, the Local Group contains approximately 134 confirmed members. That might sound like a dense neighbourhood. It is not. The vast majority of those members are tiny dwarf galaxies containing only a few billion or even a few million stars each. Many of them orbit the Milky Way or Andromeda as satellites, trapped in gravitational bondage like moons circling a planet. The third largest member, the Triangulum Galaxy, contains roughly 40 billion stars and sits about 2.7 million light-years from us. Beyond these three dominant spirals, the Local Group is mostly populated by dim, small, easily overlooked structures scattered across a volume of space, roughly 10 million light-years in diameter. 10 million light-years. That is the size of our so-called neighborhood. The distance across the local group, from one edge to the other, is approximately 100 times the diameter of the Milky Way itself. Imagine standing in your house and being told that the nearest house is 100 house lengths away, not 100 feet, 100 times the size of your entire home. That is the kind of spacing we are talking about, and this is the densest galactic environment anywhere near us. Within this vast volume, galaxies are not evenly distributed. They clump around the two gravitational anchors, the Milky Way and Andromeda, with a loose scattering of dwarfs filling the space between. Some of those dwarfs are so faint and so isolated that astronomers are still discovering them. A revised three-dimensional map of the local group, published in late 2025, catalogued 142 confirmed members and noted that discoveries continue at a steady pace, particularly of ultra-faint dwarf galaxies, hiding in the data from surveys like Gaia and the James Webb Space Telescope. The group's overall structure resembles a dumbbell, with one lobe of galaxies centered on the Milky Way and another centered on Andromeda, separated by roughly 2.5 million light-years of nearly empty space. Between those two lobes, a sparse scattering of isolated dwarfs drifts through the gravitational field of both giants, too small to anchor their own communities and too far from either center to feel truly at home. The space connecting those two lobes is not a bridge, it is a gulf, a region of near total emptiness that even the gravitationally bound members of this family must cross over timescales measured in billions of years. But here is the crucial thing about the local group that most people never consider. Even inside this gravitationally bound family, the distances between members are enormous. The Large Magellanic Cloud, one of the closest satellite galaxies to the Milky Way, sits roughly 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years distant. These are satellites of our own galaxy, gravitationally bound to us, orbiting within our extended halo, and they are still so far away that light needs hundreds of thousands of years to make the trip. The Sagittarius Dwarf Elliptical Galaxy is closer, only about 70,000 light-years from our galactic center, but it is in the process of being torn apart by the Milky Way's tidal forces. It is not a neighbor so much as a victim, a galaxy being consumed by our own. Step beyond the satellites and the gaps widen dramatically. The next nearest significant galaxies after the Magellanic Clouds and the various dwarf satellites are objects like NGC 6822, an irregular galaxy roughly 1.6 million light-years away, and IC 1613, another irregular galaxy at about 2.4 million light-years. These are small systems, faint and unremarkable in cosmic terms, and they already sit at distances that make any concept of physical connection meaningless. A beam of light sent from the Milky Way to IC 1613 would arrive after 2.4 million years. A spacecraft travelling at the Parker Solar Probe's record speed would need roughly 4 billion years. These galaxies are our neighbours, part of our own gravitationally bound family, and reaching them is already functionally impossible. What people rarely grasp is how empty the space between these galaxies actually is. When you look at a map of the local group, the galaxies appear as labelled dots on a diagram. Your brain treats the diagram the same way it treats a road map. It sees dots connected by implied routes. It assumes the space between the dots is filled with something: roads, terrain, atmosphere, medium. But the space between galaxies is not filled with anything resembling a medium. It is filled with almost nothing. The interstellar space within our galaxy, the space between stars, is already extraordinarily empty. A typical region of interstellar space contains roughly 1 million hydrogen atoms per cubic meter. That sounds like a lot until you compare it to the air you are breathing right now, which contains approximately 25 trillion molecules per cubic meter. Interstellar space is a vacuum so profound that no laboratory on Earth has ever come close to replicating it. And yet, compared to the space between galaxies, Interstellar space is practically dense. Intergalactic space contains approximately 1 atom per cubic meter. 1. In a volume of space the size of a washing machine, you would find a single hydrogen atom. The rest is void. Pure, featureless, uninterrupted nothingness stretching for millions of light years in every direction. The intergalactic medium, as astronomers call it, is one of the most rarefied environments in the known universe. According to measurements from the Harvard-Smithsonian Center for Astrophysics, this material has a density less than a billionth of the density of air at sea level. That is not emptiness in the casual sense. That is emptiness so extreme it challenges the meaning of the word exist. Intergalactic space is roughly 1 million times emptier than the space between stars. That is not a gradual increase. That is a chasm. If interstellar space is a desert, intergalactic space is a desert the size of a continent with nothing in it but a single grain of sand. The jump from interstellar to intergalactic is not a step up the same ladder. It is a leap to a completely different category of emptiness, a void so extreme that it severs any physical or intuitive connection between the structures it separates. Think about what that density means in practical terms. If you could somehow scoop up all the matter in a cube of intergalactic space 1 million kilometers on a side, a cube large enough to swallow our suns several times over, you would collect a quantity of material so small it would be invisible to the naked eye. The void between galaxies is not just empty, it is a near-perfect vacuum on a scale that dwarfs anything in human experience. The best vacuum chambers on Earth, the ones used in semiconductor fabrication and particle physics, contain roughly 10 trillion molecules per cubic meter. Intergalactic space is 10 trillion times emptier than that. It is a void so thorough that it barely qualifies as part of the physical universe. And the temperature of this void does not help. The intergalactic medium, despite containing almost nothing, registers temperatures of millions of degrees. This sounds contradictory until you understand that temperature in physics describes the average kinetic energy of particles, not how hot something would feel. With so few particles per cubic meter, there is no meaningful transfer of heat. You could float in intergalactic space and freeze to death surrounded by particles technically hotter than the surface of the sun. The void between galaxies is simultaneously scorching and frozen, energetic and lifeless, technically filled and practically empty. It is a place where the normal categories of physical experience break down entirely, where the concepts of hot and cold, full and empty, lose their intuitive meanings and become technical labels applied to conditions no human was ever meant to encounter. This is the environment that separates every galaxy from every other galaxy. Not a corridor, not a passage, not a medium through which you could travel with sufficient technology. A wasteland of such staggering emptiness that it makes the vacuum between stars look like a crowded marketplace by comparison. And this wasteland extends for millions of light years between even the closest galactic neighbours. The reason this matters, the reason it transforms intergalactic distance from a number into a horror, is that the emptiness changes the nature of the separation. When we talk about distances within our galaxy, we are talking about gaps between objects embedded in a shared structure. Stars within the Milky Way are part of the same gravitational system. They orbit the same centre. They are embedded in the same interstellar medium, the same magnetic fields, the same cosmic ray environment. A journey between two stars within our galaxy is a journey through something. Thin, sparse, unimaginably diffuse, but something. There is a continuity between origin and destination. They belong to the same place. Intergalactic space severs that continuity completely. The gap between the Milky Way and Andromeda is not a long hallway connecting two rooms. It is an ocean with no water. There is no shared structure, no continuous medium, no gravitational bridge you can follow from one galaxy to the next. The galaxies float in isolation, separated by voids so absolute that the word between barely captures the reality. It is not the space between two things, It is the absence of anything connecting them at all. And this is the local group. This is the tightest, most gravitationally intimate galactic association anywhere in our cosmic vicinity. These galaxies are bound to one another. They will eventually interact, merge, reshape one another through gravitational forces playing out over billions of years. If any galaxies in the universe can be called connected, it is these. And yet even here, even among gravitational partners confirmed to be falling toward each other, the distances are so large and the void so absolute that the concept of proximity loses all human meaning. Now consider what lies beyond. The local group is not the end of the story, it is the beginning. The nearest galaxy cluster of any significant size is the Virgo cluster, sitting roughly 54 million light-years away. That distance is more than 20 times the gap between the Milky Way and Andromeda. Beyond Virgo lie other clusters, other superclusters, other walls and filaments of galaxies stretching across hundreds of millions and billions of light-years. The observable universe contains an estimated 2 trillion galaxies spread across 93 billion light-years of cosmic diameter. And between all of those galaxies, threading through every gap, filling every void, lies the same intergalactic wasteland, the same near-perfect vacuum, the same atoms per cubic meter desolation stretching to horizons that light itself has not yet had time to reach. The photographs lied to you. The universe is not crowded, it is not full, it is not a bustling metropolis of galaxies scattered across a navigable space. It is a scattering of isolated islands separated by oceans so wide and so empty that the islands might as well exist in separate realities. The galaxies are there, you can see them, you can photograph them, you can count them in the trillions. But the space between them turns every one of those galaxies into a prisoner of its own location, surrounded by a void so vast that even light, the fastest messenger in the cosmos, needs millions of years to carry a single photon from one shore to another. And what makes this truly terrifying is not the distance itself, it is what the distance implies. If the nearest major galaxy is already 2.5 million light-years away, across a void containing 1 atom per cubic meter, then what does closeness even mean at this scale? What does neighborhood mean? What does connection mean? The local group is the most connected galactic environment we know, and its members are already so far apart that no signal, no spacecraft, no technology conceivable under current physics could bridge the gaps within any meaningful time frame. The universe did not scatter its galaxies carelessly. It arranged them in a pattern of isolation so extreme that even their gravitational partnerships play out across timescales measured in billions of years. The Milky Way and Andromeda are falling toward each other right now, confirmed and measured beyond any doubt, and they still will not meet for billions of years more despite already being locked in mutual gravitational attraction. 2 galaxies that the universe itself has bound together, 2 structures actively collapsing toward one another under the pull of mutual gravity, and they are still so far apart that their reunion will outlast the remaining life of our sun. That is the first shock. Galaxies that we call neighbours, galaxies visibly approaching one another, galaxies that may well collide, are still separated by chasms so wide that their merger requires more time than our star has left to burn. But the true emptiness between them, the nature of that void, the absence of anything filling the space they must cross, that is a story with far darker implications than most people are prepared to confront. And it begins with understanding what intergalactic space actually is, not as a concept on a diagram, not as a blank stretch on an artist's rendering, but as a physical environment more hostile, more barren, and more overwhelmingly empty than most people have ever been asked to imagine. So the distances have been established. Now forget the numbers. Forget the light years and the quintillions of miles. Instead, imagine you are there. You have been transported to a point in space exactly halfway between the Milky Way and the Andromeda galaxy, roughly 1.25 million light years from either shore. You float in your suit. Your instruments work, your eyes adjust, and what you see is nothing. Not nothing in the poetic sense, Not nothing in the way a dark room feels empty. Genuine structural nothing. There are no stars, not one. The nearest individual star in any direction is so far away that its light is too faint to register, even as a dim point. The Milky Way behind you would appear as a pale, hazy smudge, a ghostly oval smaller than your thumbnail held at arm's length. Andromeda ahead would look similar, a faint grey glow with no resolved detail. Between those two smudges, in every other direction you look, the sky is black. Not the comfortable darkness of a clear night on Earth where thousands of stars provide a canopy of light. An absolute, featureless, unyielding blackness that extends in every direction without interruption. No nebulae, no star clusters, no comets or planets, no milky band of galactic light. Just the void. Your instruments confirm what your eyes already suspect. There is functionally nothing here. The material surrounding you is so sparse that your senses register it as indistinguishable from a perfect vacuum. You could extend your arms in every direction and sweep through a volume of space larger than a building without your gloves touching a single atom. The loneliness of this place is not metaphorical, it is physical. It is baked into the atomic structure of the space itself. You are floating in the most desolate environment the universe can produce, and it stretches outward from your position for over 1 million light years in every direction before anything resembling structure begins to emerge. This is not a theoretical exercise. The conditions are real. If you could somehow survive the journey and arrive at this midpoint, the visual experience would be unlike anything a human being has ever confronted. On Earth, even in the darkest desert on the darkest night, your eyes can detect the Milky Way overhead, a faint band of combined starlight from billions of suns. In intergalactic space, that band is gone. There is no ambient glow from any direction except the two faint smudges of the galaxies themselves. The cosmic microwave background radiation, the faint afterglow of the Big Bang, permeates the space around you, but its wavelength is far too long for human eyes to detect. As far as your senses are concerned, you exist in a darkness more complete than anything that occurs naturally on any planet orbiting any star. You could wait 1 billion years in this location and nothing would change. No star would drift close enough to become visible, no nebula would form, no light would appear. The void is patient and permanent. This is intergalactic space. Not a gap, not a pause between interesting things. A place, an environment with its own physical properties, its own character, its own terrifying identity. And understanding what this place actually is, understanding what fills it and what does not, is the key to grasping why the distance between galaxies is not merely large, but qualitatively different from any other kind of cosmic separation. The intergalactic medium is not truly empty in the absolute sense. Physicists discovered decades ago that the space between galaxies contains a thin, diffuse material spread across the cosmic volume. This material has a name, the warm-hot intergalactic medium, and it is one of the most elusive substances in the observable universe. Cosmological simulations predicted its existence long before anyone detected it directly. The models showed that as the universe evolved and galaxies formed, enormous quantities of ordinary matter should have been shock-heated during the process of gravitational collapse. Gas falling toward the dense regions of the cosmos would slam into other infalling gas at tremendous speeds, generating shockwaves that heated the material to temperatures between 100,000 and 10 million degrees. This heated plasma would then settle into the filamentary structure of the cosmic web, threading between galaxies in vast, tenuous streams, too hot to form stars and too diffuse to glow visibly. For years, this material was essentially missing. Astronomers could account for the ordinary matter locked inside galaxies, inside stars, inside planets and gas clouds. They could measure the matter in galaxy clusters, where hot gas glows in X-rays. But when they added it all up, roughly half the ordinary matter the universe should contain was unaccounted for. The numbers from the cosmic microwave background, the afterglow of the Big Bang, told scientists exactly how much normal matter the universe produced. The numbers from direct observation told them where only about half of it ended up. The rest had vanished into the void between galaxies. The warm, hot intergalactic medium was the answer. In 2018, observations of highly ionized oxygen atoms in the spectra of distant quasars provided strong evidence that this diffuse plasma exists along the lines of sight between Earth and faraway light sources. In 2020, measurements of dispersion from fast radio bursts, brief pulses of radio energy from distant galaxies, further confirmed that the missing ordinary matter resides in the intergalactic medium, spread across the cosmic web in quantities consistent with theoretical predictions. Roughly 40 to 50% of all the normal matter in the universe, every proton, every neutron, every electron that is not already inside a galaxy, appears to be suspended in this hot, impossibly thin haze stretching between the structures of the cosmos. And here is the part that makes this discovery so devastating for any hope that intergalactic space might be less empty than it appears. Even with all that missing matter accounted for, even with half the universe's ordinary atoms distributed through the intergalactic medium, the density remains staggeringly low. The warm, hot intergalactic medium is expected to contain between 1 and 10 particles per cubic meter in its densest filamentary regions. In the deep voids between those filaments, the density drops even lower. You could fill a volume of intergalactic space equal to the entire Earth, and the total mass of ordinary matter inside that sphere would weigh less than a large commercial aircraft. The missing baryons are not missing because they are hiding somewhere dense. They are missing because they are spread so unimaginably thin that detecting them at all required decades of technological advancement and some of the most sensitive instruments ever built. To appreciate the scale of this thinness, consider a comparison. The air in the room where you are sitting right now contains roughly 25 trillion molecules in every cubic meter. A cubic meter of interstellar space inside the Milky Way contains about 1 million particles. A cubic meter in the densest part of the warm, hot intergalactic medium, inside a cosmic filament, contains perhaps 10 particles. And in the deep voids between filaments, even that sparse population fades toward fractions of a single particle per cubic meter. The progression from breathable air to intergalactic void represents a decrease in density spanning roughly 25 orders of magnitude. That is a factor of 10 trillion. No analogy can faithfully capture a ratio that large. It is like comparing the mass of the sun to the mass of a single bacterium, and then saying the bacterium is too heavy. The warm, hot intergalactic medium does not make the void between galaxies feel any less empty. It makes it feel more tragic. The universe took half its ordinary matter and smeared it across volumes so vast that the matter became functionally invisible. It heated this material to millions of degrees and then dispersed it so thinly that it cannot form anything. No stars, no planets, no chemistry, no structure. Just an ethereal plasma haunting the darkness between galaxies, like a ghost of the matter that might have been something if it had not been scattered across an emptiness too large to allow it to collapse. But the warm, hot intergalactic medium is only the luminous fraction, the ordinary matter component. The majority of mass between galaxies is not ordinary matter at all, it is dark matter. Invisible, undetectable by any electromagnetic instrument, interacting with ordinary matter only through gravity. It constitutes roughly 85% of all matter in the universe, outweighing ordinary atoms by a ratio of roughly 5 to 1. Yet despite its dominance, it remains completely invisible to every telescope ever built. Dark matter forms the scaffolding upon which the entire visible universe is built, and its distribution reveals something profound about the architecture of cosmic emptiness. Dark matter does not scatter randomly through space. It organized itself very early in the universe's history into a vast three-dimensional network that cosmologists call the cosmic web. This structure is not a metaphor. It is a physical reality confirmed through decades of observation, simulation, and gravitational lensing measurements. The cosmic web consists of 4 distinct components, each playing a specific role in the architecture of the universe. Dense nodes sit at the intersections where multiple streams of matter converge. These nodes are where galaxy clusters form, the largest gravitationally bound structures in existence, containing thousands of galaxies and masses, equivalent to quadrillions of suns. Connecting the nodes are filaments, long, thin threads of dark matter and gas that stretch across tens or hundreds of millions of light years. These filaments serve as the highways of cosmic structure, channeling matter from low-density regions toward the dense nodes where galaxy clusters grow. Where filaments intersect at broad angles, they form walls, sheet-like concentrations of galaxies and dark matter that can extend across hundreds of millions of light years while remaining remarkably thin in the perpendicular direction. And then there are the voids. Cosmic voids are the dominant feature of the universe. They are not small gaps between clusters. They are enormous, roughly spherical regions of space where the density of matter drops far below the cosmic average. Typical voids measure between 30 and 300 million light-years across. The largest confirmed supervoids exceed 300 million light-years in diameter, and collectively, they account for approximately 80% of the total volume of the observable universe. 80%. That number deserves to be repeated because it redefines what the universe fundamentally is. When you look at a photograph of the cosmos and see galaxies scattered across the frame, you are seeing the 20%, the bright parts, the exceptions, the thin walls and narrow filaments where matter managed to concentrate. The other 80%, the overwhelming majority of the universe by volume, is void, empty, dark, structureless. The universe is not a room full of galaxies. It is an ocean of emptiness with galaxies clinging to its surface like foam on the waves. The Botes void is one of the starkest examples of this cosmic architecture, discovered in 1981 by astronomer Robert Kirshner and his team during a survey of galactic redshifts. The Botes void is a roughly spherical region of space, approximately 330 million light-years in diameter. It sits about 700 million light-years from Earth in the direction of the constellation Boötes. Inside this enormous volume, astronomers have found approximately 60 galaxies. 60. In a region where the cosmic average would predict roughly 2,000. The Botes void is so empty that if the Milky Way sat at its center, humans would not have discovered the existence of other galaxies until the 1960s. When telescope technology finally became powerful enough to detect objects at the distances required to see beyond the void's boundaries. For most of human history, looking out from the center of the Botes void, the sky would have appeared to contain nothing but our own stars. The universe beyond would have been invisible. The very concept of other galaxies would have seemed absurd. The few galaxies that do exist inside the Botes void are clustered in a thin, tube-shaped region running through its center, as though they were clinging to one final thread of structure within the emptiness. These void galaxies tend to be small, isolated, and slowly evolving. Without nearby neighbors to interact with, without the gravitational collisions and mergers that drive evolution in denser environments, they drift through the void in a state of cosmic stasis. They are among the loneliest objects in the known universe. Think about what that means for the history of science. The entire revolution in human understanding that began with Edwin Hubble's discovery that the universe contains other galaxies, a discovery that shattered humanity's belief that the Milky Way was the entirety of existence, would never have occurred. A civilization inside the Botes void would have looked outward and seen nothing beyond its own galaxy. Its cosmology would have stalled at the threshold of the greatest truth in astronomy, because the universe around it was too empty to reveal that truth. The void would not just isolate a galaxy physically, it would isolate it intellectually, hiding the very existence of the larger cosmos behind a wall of emptiness too deep for telescopes to penetrate. The Botes void is not unique. It is simply one of the largest known examples. The universe is riddled with voids of varying sizes. The KBC void, the structure in which our own Milky Way appears to reside, stretches approximately 2 billion light-years across, with a density roughly 20% lower than the cosmic average. The local void, an emptier region adjacent to our own galactic neighborhood, extends roughly 200 million light-years and has been shown to influence the motion of our galaxy, pushing us away from its center at hundreds of thousands of miles per hour. Wherever astronomers point their instruments and map the three-dimensional distribution of galaxies, they find the same pattern. Matter concentrates into thin filaments and walls, and between those structures lie enormous bubbles of almost nothing. The way these voids formed tells a story about the universe's fundamental character. In the first few 100,000 years after the Big Bang, matter was distributed almost uniformly across all of space. Almost, but not perfectly. Tiny quantum fluctuations in the density of the infant universe, variations of roughly 1 part in 100,000, created regions that were ever so slightly denser or slightly less dense than average. Gravity took over from there. Regions with slightly more matter pulled in additional material from their surroundings, growing denser over time. Regions with slightly less matter lost material to their denser neighbors, becoming emptier. Over billions of years, this process of gravitational instability amplified those minuscule initial differences into the dramatic cosmic web we observe today. Dense regions collapsed into the filaments and nodes where galaxies formed. Underdense regions expanded into the voids. The cosmic web is gravity's autobiography, written in the distribution of matter across the largest scales the universe can offer. The quantum fluctuations that seeded the voids were unimaginably small. A variation of 1 part in 100,000 is so slight that if you represented the average density of the early universe as a perfectly flat lake, the fluctuations would correspond to ripples less than a millimeter high on a surface stretching from one end of the Earth to the other. Yet those infinitesimal ripples, amplified by gravity over 13.8 billion years of cosmic evolution, became the voids and filaments and clusters that define the structure of everything we can observe. The largest empty spaces in the universe trace their origin to the smallest possible variations in the density of the newborn cosmos. But what makes this architecture so isolating is the relationship between the structures and the voids. Galaxies do not sit in the middle of comfortable volumes of space surrounded by other galaxies at manageable distances. They perch on the edges of enormous empty bubbles. The filaments where galaxies concentrate are thin. Cosmological surveys show that typical filaments measure only about 20 million light-years in width, while stretching across hundreds of millions of light-years in length. They are cosmic threads, disproportionately long and impossibly narrow compared to the voids they border. A galaxy sitting on one side of a void and looking across to the nearest filament on the other side might face a journey of 100 million light-years or more through a region containing almost no matter at all. And the voids are not passive, they are growing. Cosmic expansion stretches all of space, but the effect is most dramatic in regions where there is little gravity to resist it. In dense filaments and galaxy clusters, gravitational attraction slows or halts the expansion locally. Galaxies and clusters remain gravitationally bound to one another. But inside voids, where matter is sparse and gravity is weak, dark energy drives accelerating expansion essentially unopposed. Voids are expanding faster than the cosmic average. They are growing larger, becoming emptier, and pushing galaxies on their borders farther apart. The cosmic web is not a static structure. It is a dynamic architecture in which the voids are winning. The empty spaces are consuming an ever greater share of the cosmic volume, and the filaments between them are slowly thinning. This means the isolation between galaxies is not a fixed condition. It is worsening. The voids that separate galaxies today will be larger tomorrow, and larger still a billion years from now. The filaments that connect clusters will stretch thinner. The walls that border the voids will become more diffuse. Dark energy is reshaping the cosmic web in real time, slowly dissolving the connections between structures and enlarging the empty spaces that divide them. The universe is not merely empty, it is becoming emptier. The architecture of isolation is deepening with every passing era of cosmic time. This is the environment that intergalactic distance must be understood within. The gap between galaxies is not a featureless blank space of uniform emptiness. It is a structured emptiness, organized by the cosmic web into regions of varying desolation. Some directions from any given galaxy lead along a filament, where the next galaxy might be found within a few million light-years, close by intergalactic standards. Other directions lead straight into a void, where the nearest galaxy in that direction might be tens or hundreds of millions of light-years away. The universe is anisotropic in its isolation. Depending on which way you look from any given galaxy, the depth of the emptiness changes dramatically. Consider what this means for a galaxy sitting on the edge of a supervoid. That galaxy looks outward in one direction and sees the filament it belongs to, a thin ribbon of light and matter stretching toward the nearest cluster. In the other direction, it sees nothing. A gulf of emptiness extending for hundreds of millions of light-years. No stars, no galaxies, no structure of any kind. Just an expanding void that grows larger with every passing moment. The galaxy is not surrounded by other galaxies. It is half surrounded by a thin band of structure and half surrounded by an abyss. Even within the filaments themselves, the spacing between galaxies is not what most people imagine. Galaxies in a typical filament are separated by distances measured in millions of light-years. They do not cluster tightly like beads on a string. They are spread along the filament with enormous gaps between them. Gaps that are small compared to the voids on either side, but still impossibly large by any human measure. A galaxy travelling along a filament toward the nearest cluster would pass through millions of light-years of thinning gas and dark matter before reaching the next significant concentration of stars. The filament provides a direction but not a road. It is a vague gravitational guideline stretching across distances that would take light millions of years to traverse. The cosmic web also reveals why intergalactic space feels qualitatively harsher than the space between stars. Within a galaxy, stars are separated by light-years, but they are embedded in a shared gravitational structure. They orbit a common center. They are bathed in the same radiation field, the same magnetic environment, the same interstellar medium. The space between stars is empty compared to planetary surfaces, but it is rich compared to what lies between galaxies. The interstellar medium contains gas, dust, cosmic rays, magnetic fields, and the faint glow of starlight from billions of surrounding suns. It is a medium in the truest sense, a substance through which energy and matter can propagate, interact, and evolve. The intergalactic medium has none of this richness. There is no starlight in the deep void between galaxies, no magnetic field strong enough to shape particle motion over meaningful distances, no dust to scatter or absorb radiation, no cosmic rays at significant densities. The faint, warm, hot plasma that threads through the filaments is too diffuse to constitute an environment in any meaningful sense. It cannot carry sound, it cannot transmit pressure waves, it cannot sustain chemistry. It is matter in name only, a population of particles so sparse that each atom exists in effective isolation from every other atom, separated by distances that might as well be infinite on any atomic scale. This is why the jump from interstellar to intergalactic is not a quantitative increase, but a qualitative transformation. Inside a galaxy, you are in a place. Between galaxies, you are in an absence. The material conditions change so drastically that the physics governing your environment shifts from the familiar to the extreme. Inside a galaxy, gravity dominates locally, pulling matter together, forming stars, building structure. In the deep intergalactic void, dark energy dominates. Gravity is too weak to organize anything. Expansion is all that happens. Matter does not clump, structure does not form. The void simply grows, stretching the already thin material ever thinner, pushing the already distant walls ever farther away. And this transformation happens not at some exotic boundary far from galactic shores. It begins almost immediately. Step outside the gravitational influence of the Milky Way, cross beyond the virial radius where matter is no longer bound to our galaxy, and within a relatively short distance by cosmic standards, you enter a regime where the rules change. The interstellar medium thins, the stellar density drops to zero, the gravitational influence of the galaxy fades, and you find yourself in the intergalactic medium, an environment governed not by the familiar forces that build worlds and stars, but by the slow, implacable expansion of space itself. The cosmic web makes one more thing devastatingly clear. The universe's emptiness is not an accident. It is not a temporary condition that will resolve as galaxies spread out and fill the gaps. The voids exist because the physics of the universe requires them. Gravity creates structure by pulling matter out of underdense regions and concentrating it into overdense ones. The very process that builds galaxies and clusters also evacuates the space between them. You cannot have one without the other. Every filament exists because a void was emptied to create it. Every galaxy shines because the matter that forms its stars was pulled from a region that was left darker and more barren as a result. The structure and the emptiness are two expressions of the same gravitational process. They are inseparable, and the emptiness always wins on volume. 80% of the universe is void. The other 20% is structure, and most of that structure is thin filaments barely holding their territory against the expanding darkness on either side. Galaxies are not sprinkled across the universe like sugar on a table. They are stranded on the narrow ridges of a vast foam, separated by bubbles of emptiness so large that the ridges themselves seem fragile and impermanent by comparison. The Milky Way sits on one such ridge, part of a filament connected to a wall connected to a supercluster, and on either side of that thin line of structure yawn voids that dwarf everything we have ever seen or mapped or named. This is the architecture of the universe, not a crowded ballroom of galaxies dancing at conversational distances, a foam of darkness punctuated by thin films of matter, where galaxies cling to the surfaces of enormous empty bubbles and look out across gulfs so wide that even light, travelling since before our species existed, has not yet crossed them. The emptiness is not a bug in the cosmic design, it is the design. The voids are not holes in the structure, they are the structure. And the galaxies, for all their billions of stars and all their trillions of planets, are just a thin, luminous residue clinging to the edges of an architecture built primarily from nothing. What this means for any hope of crossing from one galaxy to another, what it implies for communication, for travel, for any form of cosmic connection between the islands of light, is a question with answers that grow darker at every scale. And those answers begin to emerge when you stop asking how far it is and start asking what it would actually take to get there. There is a moment in every confrontation with intergalactic distance where the mind shifts from understanding to surrender. The numbers have been established. The emptiness has been described. But what truly breaks human intuition is not the distance or the void. It is the realization that no amount of technology, no feat of engineering, no breakthrough in physics as we currently understand it, can overcome what the universe has placed between its galaxies. Intergalactic distance does not merely make travel difficult. It makes travel, communication, and contact functionally impossible across the overwhelming majority of the cosmos. And the reason goes deeper than most people suspect, because the universe is not simply large, it is actively working against any attempt to cross the gaps. Start with the most generous scenario imaginable. Forget the limitations of current technology. Forget chemical rockets, ion drives, solar sails. Imagine that a civilization has solved every engineering challenge and built a spacecraft capable of travelling at a significant fraction of the speed of light, say 90%. This is not a realistic prospect for humanity in the foreseeable future, but grant it anyway for the sake of argument. A ship moving at 90% of light speed would be the most extraordinary machine ever conceived. It would cross the distance from Earth to the Sun in about 9 minutes. It would leave the solar system in hours. It would reach the nearest star in under 5 years. Now point that ship toward the Andromeda galaxy and fire the engines. At 90% of the speed of light, the journey to Andromeda would take approximately 2.8 million years as measured by an observer watching from Earth. The ship itself, thanks to relativistic time dilation, would experience a shorter journey. At 90% of light speed, the dilation factor compresses onboard time by roughly a factor of 2.3. The crew, if somehow kept alive, would experience the passage of about 1.2 million years. This is not a rounding error. It is a duration that exceeds the entire span of the genus Homo on Earth. Every human ancestor who ever lived, from the first toolmakers to the last person born before the ship launched, would fit inside a fraction of the onboard travel time. The journey does not merely exceed a human lifetime, it exceeds the lifetime of the entire human lineage. What if the ship travelled faster? At 99% of the speed of light, time dilation compresses the onboard experience more aggressively, by a factor of about 7. The crew would experience roughly 350,000 years, still an eternity, still longer than modern humans have existed. At 99.9% of light speed, the dilation factor rises to about 22, reducing onboard time to approximately 113,000 years. Better, but still a span during which entire civilizations could rise, flourish, collapse, and be forgotten dozens of times over. Even at 99.99% of light speed, a velocity so extreme that the energy required to achieve it verges on the total mass energy of the spacecraft itself, the crew would still experience tens of thousands of years of travel. No version of this calculation produces a human-scale journey. The distance is simply too enormous for even the most extreme relativistic effects to compress it into anything manageable. And this is the optimistic case. This assumes a ship travelling at a velocity that would require energy inputs beyond anything physics currently allows at practical scales. Accelerating even a modest spacecraft to 90% of light speed demands energy quantities that dwarf the total output of human civilization. The kinetic energy of a single kilogram of matter moving at that speed is approximately 117 quadrillion joules. For a spacecraft large enough to carry fuel, shielding, and any form of life support, the energy budget climbs toward values that can only be expressed in terms of stellar output. You would need to capture and convert a meaningful fraction of an entire star's energy to accelerate a ship to the speed required for an intergalactic crossing, and then capture and convert it again to decelerate on the other side. The engineering is not merely difficult, it sits at the boundary between ambitious and physically absurd. To put the energy problem in concrete terms, the total energy consumption of all human civilization in a single year is approximately 580 exajoules. Accelerating a modest 10,000 kilogram spacecraft to 90% of light speed would require roughly 1.2 times 10 to the 21st joules, an amount equivalent to more than 2,000 years of total human energy production. For a ship massive enough to sustain a crew, the figure climbs by orders of magnitude. And this calculation assumes perfect efficiency, no waste heat, no losses, every joule of energy converted directly into kinetic motion. Real propulsion systems are nowhere near that efficient. The gap between what we can build and what intergalactic travel demands is not a gap that incremental improvement can close. It is a chasm that requires fundamentally new physics to even begin to address. But even if that problem were solved, even if a civilization harnessed the energy of its star and built the impossible ship, the journey itself would render the mission meaningless in almost every practical sense. At 90% of light speed, the ship would arrive at Andromeda after more than 1 million years of onboard time. No biological organism known to science can survive a duration remotely approaching that span. No mechanical system built from known materials can remain functional across geological timescales without maintenance, repair, and replacement. The ship would need to be not a vessel but a self-sustaining world capable of enduring longer than most species persist on Earth. It would need to carry not passengers, but a civilization, one that could reproduce, evolve, and maintain its technological infrastructure across thousands of generations. The crew that arrived at Andromeda would bear no meaningful resemblance to the crew that departed. They would be a different species, shaped by 1 million years of isolated evolution in a metal shell crossing the void. and the civilization they left behind would be gone. 2.8 million years would pass on Earth between departure and arrival. Whatever culture launched the ship would have transformed beyond recognition or vanished entirely long before the first signal came back. There would be no one to receive the report, no one to celebrate the achievement. The ship would arrive at a galaxy full of 1 trillion unfamiliar stars, carrying the descendants of a civilization that no longer existed, reporting to a home that had forgotten they were coming. The distance does not just separate locations, it separates eras. It turns every intergalactic journey into a one-way trip through time as well as space. This is the scenario for the nearest large galaxy. Andromeda is the easiest target. It is the closest major spiral, the best-case mission. For galaxies beyond the local group, the numbers escalate into outright absurdity. The Virgo cluster sits 54 million light-years away. At 90% of light speed, the journey would take 60 million years as measured from Earth and roughly 26 million years on board. The Coma cluster, a rich concentration of galaxies, lies 320 million light-years distant. The trip would consume over 350 million years, a duration stretching back to the early Carboniferous period on Earth, an era when shallow seas covered much of the continents and the earliest four-limbed creatures were still adapting to life beyond the water's edge. No one is crossing that distance. No technology alters the fundamental temporal cost of crossing 320 million light-years of expanding void. But the truly devastating blow to intergalactic travel does not come from distance or energy or time dilation. It comes from the universe itself. Space is expanding, not metaphorically, not in the sense that galaxies are flying apart through a static void. The fabric of space-time is stretching, increasing the distance between all points that are not gravitationally bound together. Every second, the space between galaxies grows. Every moment, the void gets wider, and the farther away a galaxy is, the faster the space between it and us expands. This relationship was first described by Edwin Hubble in 1929 and is now called Hubble's law. It states that the recession velocity of a galaxy is proportional to its distance. The proportionality constant, the Hubble constant, currently measures approximately 67 to 73 kilometers per second per megaparsec, depending on which measurement technique is used. The exact value remains a subject of active scientific debate known as the Hubble tension, but the implications of the law itself are not in dispute. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity of a galaxy increases by approximately 70 kilometers per second. At first glance, this seems modest, 70 kilometers per second per megaparsec, but the effect compounds with distance. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. And the speed of light is approximately 300,000 kilometers per second. This means that at a distance of roughly 14 billion light-years, the recession velocity of a galaxy equals the speed of light. Beyond that distance, galaxies recede faster than light. This does not violate Einstein's theory of relativity. Relativity prohibits objects from moving through space faster than light. It says nothing about space itself, stretching at any rate it pleases. Galaxies beyond the Hubble radius are not moving through space at superluminal velocities. They are sitting relatively still in their local patch of space-time, while the space between us and them expands faster than light can cross it. The distinction is technical, but the consequence is absolute. You might assume this means those galaxies are forever beyond our reach, but the physics is more subtle and, ultimately, more devastating. Many of the galaxies we observe today were receding faster than light when they emitted the photons now reaching our telescopes. In a decelerating universe, light from beyond the Hubble radius could eventually catch up as expansion slowed. But our universe is not decelerating. It is accelerating. Dark energy ensures the expansion speeds up rather than slowing down, and that acceleration creates a grimmer boundary. The cosmic event horizon is the true line of no return. The distance beyond which light emitted now will never reach us, no matter how long the universe endures. It currently sits at approximately 16 to 18 billion light-years. That sounds like it encompasses a vast volume of space. It does not. The observable universe extends 46.5 billion light-years in every direction. The reachable universe, the portion we could theoretically still touch if we departed at light speed right now, is a small bubble inside that larger sphere. Current estimates suggest that only about 6% of the galaxies within the observable universe remain theoretically reachable. The other 94% are already gone. They are receding too fast. Space between us and them is expanding too rapidly. Even light cannot catch them. They are visible but untouchable, observable but permanently isolated from any form of contact. 94%. Out of the estimated 2 trillion galaxies in the observable universe, approximately 1.9 trillion of them are already beyond the reach of any signal, any ship, any message we could ever send. Even at the speed of light, even starting today, they exist. We can see them. Their light is still arriving. Photons that began their journey billions of years ago when the galaxies were closer and the expansion had not yet carried them past the horizon of reachability. But those galaxies, as they exist right now, are forever beyond our reach. The light we see from them is a fossil, a record of where they used to be when the universe was younger and smaller. The galaxies themselves have long since crossed the boundary into permanent isolation. To make that number visceral, consider that the Milky Way alone contains somewhere between 200 billion and 400 billion stars. It is one galaxy. The 1.9 trillion galaxies we can never reach contain, collectively, somewhere in the neighborhood of 100 sextillion stars. Each of those stars may host planets. Each of those planets may harbor conditions suitable for chemistry, for biology, for the emergence of life or intelligence. And every single one of them is forever sealed behind a horizon of expanding space that no signal, no ship, no thought experiment can penetrate. Whatever exists out there, whatever civilizations may have arisen, whatever wonders may have been built, they are as inaccessible to us as if they existed in a separate universe entirely. In every practical sense, they do, and the situation is getting worse. Dark energy, the mysterious force driving the acceleration of cosmic expansion, ensures that the reachable universe shrinks with every passing moment. Galaxies that are currently within the cosmic event horizon will eventually cross beyond it as the expansion carries them farther away. With every year that passes, hundreds of millions of additional stars slip beyond the reachability threshold. Entire galaxies are crossing the boundary and vanishing from the set of objects we could ever theoretically contact. The reachable universe is not stable. It is contracting, slowly but relentlessly, as dark energy pushes the cosmos apart at an accelerating rate. The endpoint of this process is total isolation. Current models project that within 100 to 150 billion years, every galaxy outside the local group will have receded beyond the cosmic event horizon permanently. The Milky Way, Andromeda, and the rest of our gravitationally bound family will have merged into a single structure surrounded by an expanding darkness that no telescope could ever penetrate. What that final loneliness will look like, what it will mean for any civilization that inherits it, is a question that demands its own reckoning. This process has a name among cosmologists. They call it the shrinking of the cosmic horizon. It is one of the most counterintuitive predictions of modern cosmology. In our everyday experience, horizons expand as we climb higher or move faster. From the top of a mountain, you can see farther. In a faster airplane, you can reach more destinations. The cosmic horizon does the opposite. As time passes, the boundary of what we can reach contracts rather than expands. The universe gets bigger, but our accessible share of it gets smaller. We are not exploring an expanding frontier. We are watching a closing door. This future is not speculative. It is the direct consequence of observations we have already confirmed. Dark energy is real. Cosmic acceleration is measured. The expansion rate is known. The math leads to one conclusion. The universe is systematically cutting off every connection between its largest structures. One by one, galaxy by galaxy, the cosmos is isolating itself, dismantling the bridges of light that currently allow us to see across billions of light years and replacing them with an expanding darkness that no signal can penetrate. Now consider what this means for communication. Even within the small fraction of the universe that remains reachable, sending a message to the nearest large galaxy, Andromeda, would take 2.5 million years at the speed of light. A response, if anyone were listening, would take another 2.5 million years to return. A single round-trip exchange would consume 5 million years. No conversation is possible. No negotiation, no cultural exchange, no alliance, no warning. The communication delay turns every interaction into a monologue, delivered to an audience that may not exist by the time the words arrive. For galaxies beyond the local group, the situation is qualitatively worse. A message sent to the Virgo cluster would take 54 million years to arrive. By the time a reply could return, 108 million years would have elapsed. A message to the Coma cluster would take over 600 million years for a round trip. These are not communication timescales. They are geological timescales. They are intervals long enough for entire branches of the evolutionary tree to appear and go extinct. They are long enough for continents to reshape themselves, for oceans to open and close, for the very chemistry of Earth's atmosphere to transform. Sending a radio signal to a galaxy 300 million light-years away is not like mailing a letter to a distant country. It is like carving a message on a stone and burying it for a future species to find after your entire civilization has been forgotten. And even this grim picture understates the problem, because the messages themselves face an additional enemy. Cosmic expansion stretches the wavelength of any signal in transit. A radio transmission sent at a specific frequency will arrive at its destination with a longer wavelength and lower energy than it started with. Over millions or billions of light-years of travel through expanding space, this redshift accumulates. A signal that began as a tight, coherent radio beam will arrive as a faint, stretched whisper at frequencies that may not even be detectable by the receiving civilization's instruments. Assuming any such civilization exists and is listening, the expansion of space does not merely delay the message, it degrades it. Over sufficient distances, it erases the message entirely, stretching the signal to wavelengths so long that it becomes indistinguishable from the background noise of the cosmos. Consider a practical example. If a civilization in the Virgo cluster transmitted a powerful radio signal toward us today, at a frequency of 1000 megahertz, the signal would arrive at Earth in 54 million years. But during that transit, the expansion of space would stretch the signal's wavelength. Over 54 million light-years of expanding space, the redshift would be small but measurable. For more distant galaxies, the effect becomes crippling. A signal from a galaxy 1 billion light-years away would arrive with its wavelength stretched by roughly 7%. A signal from 5 billion light-years away would arrive stretched by roughly 40%. A signal from 10 billion light-years would arrive with its wavelength more than doubled. At some point, the stretching pushes the signal below the noise floor of any detector. The universe does not merely make long-distance calls expensive, it garbles them into silence. The universe, it turns out, is not just large and empty, it is actively hostile to connection. Every mechanism that could theoretically link one galaxy to another, travel, signaling, observation, faces a barrier that is not technological but structural. The expansion of space ensures that the vast majority of galaxies are permanently beyond contact. The energy requirements of near light-speed travel ensure that even nearby galaxies require civilizational sacrifice to reach. The time delays ensure that even successful communication spans intervals longer than species typically survive, and the redshift ensures that signals degrade and eventually vanish into the noise. This transforms the meaning of intergalactic distance. It is not a challenge to be overcome. It is a feature of the universe's design. The cosmos does not want its galaxies to be connected. That phrasing is anthropomorphic and imprecise, but it captures something real about the physics. The laws of nature, as we understand them, do not permit meaningful interaction between galaxies separated by cosmological distances. The speed of light sets an upper limit on how fast information can travel. The expansion of space ensures that most distances grow faster than that limit. Dark energy guarantees that the growth will accelerate. Together, these constraints create a universe that is not merely large but structurally partitioned, divided into islands of matter surrounded by expanding voids that no technology can bridge. The local group is our island. The Milky Way, Andromeda, Triangulum, and approximately 130 smaller galaxies comprise our gravitationally bound family. These galaxies are close enough and massive enough that their mutual gravitational attraction overcomes the cosmic expansion. They will not fly apart. They will not recede beyond the cosmic event horizon. Over the next several billion years, they will merge, interact, exchange stars and gas, and eventually collapse into a single enormous galaxy. This merged structure will be our permanent home, the only galactic community we will ever belong to. Everything else is leaving. The Virgo cluster, the nearest major galaxy cluster, is gravitationally unbound from the local group. Cosmic expansion is carrying it away. The Laniakea supercluster, the immense structure to which the local group belongs, is not a gravitationally bound system despite its name. It is a flow pattern, a region where galaxies are moving toward a common gravitational attractor, but the expansion of space will eventually overwhelm even those flows. The galaxies of Laniakea will drift apart. The supercluster will dissolve. The nodes and filaments of the cosmic web will thin and stretch and eventually snap as dark energy tears the connections between them. The universe's large-scale structure is temporary. The cosmic web is not a permanent architecture. It is a phase, a transient arrangement of matter that exists only because the universe is still young enough for gravity to compete with expansion. In the deep future, expansion wins. The web dissolves. The galaxies disperse, and each gravitationally bound island finds itself alone in an ocean of darkness that grows wider every second. This is not a failure of ambition. It is not a consequence of insufficient technology. It is a structural property of reality. The universe was not built for intergalactic connection. It was built with rules that guarantee intergalactic isolation. The speed of light creates a maximum velocity. The expansion of space creates a minimum rate at which distances grow. Dark energy creates a floor beneath which the expansion cannot fall. These three constraints, woven into the deepest physics of the cosmos, produce a universe in which galaxies are born into isolation and remain there forever. The distance between them is not a problem to be solved. It is a sentence to be served. What we observe today, the filaments and clusters and walls that seem to give the universe its shape, will not last. The forces holding them together are already losing ground to the forces pulling them apart. And what that unraveling will ultimately leave behind is something far lonelier than even the present emptiness suggests. This is the scale that breaks everything. Not merely a large distance, not merely a challenging engineering problem, a structural feature of reality that renders most of the cosmos permanently inaccessible. The gaps between galaxies are not gaps that could be crossed with better engines or more time. They are walls built from the expansion of space-time itself, growing higher and thicker with every passing era, sealing each galaxy behind a horizon that no signal can penetrate and no ship can cross. The universe contains 2 trillion galaxies. We can reach roughly 6% of them, and that number is shrinking. Every day, the reachable cosmos contracts by a volume containing millions of stars. Every century, entire galaxies cross the threshold from theoretically accessible to permanently lost. The universe is not opening up to exploration. It is closing down. It is pulling its galaxies apart, stretching the connections between them until they snap, and leaving each island of matter stranded in a void that grows without limit. The real question is no longer how far it is between galaxies. The real question is what it means to live in a cosmos where the distances between structures are not merely large but actively growing, where the very fabric of reality conspires to isolate every galaxy from every other galaxy, and where the most fundamental laws of physics guarantee that this isolation will only deepen with time. That question belongs to the final reckoning, and its answer is not comforting. Everything you have heard so far has been factual. The distances are real, the emptiness is measured, the expansion is confirmed, the unreachability is calculated from the most fundamental equations in physics. None of it is speculation, none of it is exaggeration. The universe really is this empty, this vast, this structurally hostile to connection between its largest inhabitants. And now it is time to sit with what that means. The human mind is built to find patterns, to detect relationships, to assume that visible things are connected to one another. We see a sky full of stars and we draw lines between them, inventing constellations, imagining a ceiling of light that wraps around us like a blanket. We see photographs of galaxies scattered across deep field images, and we imagine a cosmos buzzing with proximity. A universe where the distance between objects is large but fundamentally navigable. A place where the sheer abundance of galaxies implies some form of cosmic togetherness. 2 trillion galaxies. Surely a universe with 2 trillion galaxies is a full universe. Surely it is a connected universe. Surely the existence of so many structures means that isolation is impossible at the grandest scale. The word galaxy itself comes from the Greek for milk, a reference to the pale band of the Milky Way. For most of human history, we did not even know that other galaxies existed. The idea that the universe contained structures beyond our own was confirmed barely a century ago. We have known about intergalactic distance for less than 100 years. We are still learning to feel its weight. It does not. And that is the revelation that sits at the heart of everything this story has been building toward. The universe contains 2 trillion galaxies, and it is lonely. Not lonely in the sentimental sense, lonely in the structural sense. Lonely in the way an archipelago of islands scattered across an ocean 10,000 times wider than any island is lonely. The islands exist. They are real. Some of them are enormous, containing billions of inhabitants and complex ecosystems. But the ocean between them is so vast, so deep, and so featureless that the islands might as well be separate worlds. No bridge can span the water. No ship can survive the crossing. No message in a bottle can drift from one shore to another before the currents carry it into oblivion. The islands are there, and they are alone, and the ocean does not care. This analogy, like all analogies for cosmic scale, eventually breaks under its own weight, because at least on Earth, islands in the same ocean share the same water. Currents connect them, however weakly. Seabirds carry seeds between shores. Driftwood travels from one coast to another. The ocean is a medium. It transmits, it connects, even across vast distances. The intergalactic void is not a medium. It transmits nothing. It connects nothing. It is not a substance between 2 objects. It is the absence of substance, stretching across distances that make every earthly ocean look like a puddle. The archipelago analogy captures the loneliness. It cannot capture the totality of the severance. This is the architecture of the universe. Not a deficiency in it. Not a problem awaiting a solution. The architecture itself. The cosmos was not built and then emptied. It was built from emptiness. The quantum fluctuations that rippled through the infant universe 13.8 billion years ago created the initial conditions for both structure and absence, and gravity spent the next 13 billion years amplifying both. It pulled matter into filaments and nodes where galaxies could form, and it drained that matter from the regions in between, leaving behind voids so thorough that they now constitute 80% of the universe by volume. The structure and the emptiness grew together. They are the same process viewed from 2 directions. You cannot have galaxies without the voids that surrendered their matter to build them. You cannot have the cosmic web without the empty bubbles it surrounds. This means that intergalactic isolation is not an incidental feature of a universe that happens to be large. It is a necessary consequence of the physics that made galaxies possible in the first place. The same gravitational instability that formed the Milky Way also excavated the void that separates it from its neighbours. The same process that built Andromeda also ensured that the space between Andromeda and us would be swept nearly clean of matter. Every galaxy in the universe exists because a surrounding region was emptied to feed it. The birth of every island required the deepening of the ocean around it. Isolation is not the price of existence, it is the mechanism of existence. Galaxies are born isolated, and the universe ensures they stay that way. This is a difficult idea to absorb because it violates something deep in human psychology. We are social creatures. We evolved in groups. Our survival depended on connection, on cooperation, on the ability to reach others when we needed help. The idea that the universe might be fundamentally structured to prevent connection between its largest inhabitants feels almost hostile. It is not hostile. The universe has no intentions, but the effect is the same. The physics that governs cosmic structure produces isolation as reliably as the physics that governs chemistry produces water from hydrogen and oxygen. It is not a choice. It is a consequence. And the consequence is a cosmos where the most magnificent objects in existence, galaxies containing hundreds of billions of suns and trillions of worlds, are each confined to their own patch of space with no meaningful ability to interact with the others. Consider what this means for the question that haunts every discussion of cosmic scale. Are we alone? The question is usually framed in terms of biology. Is there life elsewhere? Are there other civilizations? Other minds looking up at other skies and wondering the same things? But the distance between galaxies reframes the question in a way that cuts deeper than biology ever could. Even if life is common, even if every galaxy teems with civilizations, even if intelligence is a routine product of cosmic evolution, the distances ensure that none of it matters in any practical sense. Civilizations separated by millions of light years cannot talk to each other. They cannot visit each other. They cannot confirm each other's existence within any time frame that matters to either party. They are alone in every way that the word alone has ever meant to any conscious being. A civilization in a galaxy 200 million light-years away could be the most advanced, most compassionate, most curious society the universe has ever produced. It could have solved every problem that plagues our species. It could have built wonders that would make our greatest achievements look like children's drawings. And we would never know. Not because our telescopes are too weak, not because our radios are too quiet, because 200 million light-years of expanding void sits between us, and nothing in the known laws of physics can carry a meaningful signal across that distance within the lifetime of either civilization. The void does not care how advanced either party is. It does not yield to ingenuity or determination. It is indifferent, absolute, and permanent. This asymmetry between knowledge and access is one of the most philosophically disorienting features of modern cosmology. We know the galaxies are there. We can count them. We can measure their masses, their star formation rates, their chemical compositions. We can study their evolution across billions of years of cosmic history. We know more about the observable universe than any previous generation of humans could have imagined. And all of that knowledge changes nothing about the fundamental isolation. Knowing a galaxy exists 200 million light-years away does not bring it 1 meter closer. Understanding the physics of cosmic expansion does not slow the expansion by a single kilometer per second. The knowledge and the distance coexist without the knowledge affecting the distance in any way. We are the most informed prisoners any universe has ever produced. This is the cruelty buried inside the beauty of every deep field image. When you look at a photograph showing thousands of galaxies, you are looking at thousands of islands that will never know one another. Each galaxy in that image is a complete world unto itself, containing hundreds of billions of stars, trillions of planets, and possibly countless forms of life and intelligence. And each one is sealed inside a bubble of distance and expansion that renders it permanently inaccessible to every other galaxy in the frame. The image shows proximity. The physics guarantees isolation. The beauty and the horror occupy the same frame, and there is a deeper irony still. The very technology that allows us to see those distant galaxies, the telescopes and instruments that reveal the cosmic web in all its sprawling complexity, also confirms that we can never touch any of it. Every improvement in observational capability shows us more of the universe and simultaneously demonstrates that more of it is unreachable. The James Webb Space Telescope can peer deeper into the cosmos than any instrument before it, resolving galaxies that formed when the universe was less than 500 million years old. Each of those galaxies is a real place, a collection of stars and worlds that existed and evolved and may have produced wonders beyond our imagination. And every single one of them is so far away that even light from their present state will never reach us. We are building better windows onto a cosmos that is closing its doors, and the isolation is deepening. The cosmic web is not permanent. It is a transient structure, a phase in the universe's evolution that exists only because the cosmos is still young enough for gravity to maintain the connections between its parts. Dark energy is slowly winning the contest. The voids are expanding, the filaments are thinning. The distances between galaxy groups are increasing with every passing moment, accelerating under the influence of a force that shows no sign of weakening or reversing. The cosmic web that currently connects galaxy clusters across hundreds of millions of light years will eventually dissolve, its filaments stretched beyond coherence, its walls dispersed into the expanding void. The nodes will persist for a time, gravitationally bound clusters of galaxies that hold themselves together against the tide, but even those clusters are not eternal. Given enough time, dark energy will push apart everything that is not bound into a single gravitationally locked system. The local group is our system. Recent studies have complicated the long-held certainty that the Milky Way and Andromeda will collide. Research published in 2025, incorporating updated data from the Gaia and Hubble space telescopes, and accounting for the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, found that a head-on collision within the next 10 billion years may be only about 50% likely. A subsequent 2026 analysis using the latest proper motion measurements raised the merger probability back to approximately 90%, with a median merger time of roughly 6.5 billion years. The outcome remains an active area of scientific investigation. But whether the merger happens in 5 billion years or 10, whether the two spirals collide directly or drift into a slow orbital decay, the eventual result is the same. The galaxies of the local group will combine. Their stars will mingle, their dark matter halos will merge, and over the course of tens of billions of years, the entire group will settle into a single massive structure. Astronomers have already named this future galaxy Milkomeda. Milkomeda will be enormous. It will contain the combined stellar populations of the Milky Way, Andromeda, Triangulum, and every dwarf galaxy in the local group. It will be a giant elliptical galaxy. Its elegant spiral arms are raised by the chaotic violence of repeated mergers, its stars orbiting in random directions around a massive central core. It will be, by any measure, a spectacular object, and it will be utterly, permanently, cosmically alone. Think about what that sky will look like. An observer standing on a planet in Milkomeda, perhaps orbiting a star in the merged galaxy's outer halo, would look upward and see a spectacular band of stars, the dense core of the elliptical galaxy stretching across their sky in a river of light. The view inward would be magnificent, but the view outward, beyond the galaxy's edge, would be the most terrifying sight any conscious being could confront. Nothing. Not the blackness of a cloudy night where you know the stars are hiding behind the weather. A permanent, structural emptiness. A void that contains no objects, emits no signals, and offers no evidence that anything exists beyond the galaxy's gravitational boundary. the sky would end at the edge of Milkomeda. Beyond that edge, in every direction, forever darkness. By the time Milkomeda has fully formed, roughly 10 billion years from now, every galaxy outside the local group will be receding at ever-increasing velocities. The nearest galaxy clusters will have drifted hundreds of millions of light-years farther away than they are today. The filaments of the cosmic web connecting our corner of the universe to neighbouring structures will have stretched beyond recognition, their matter dispersed into the expanding void. Within 100 to 150 billion years, every galaxy beyond the local group will have crossed the cosmic event horizon. Their light will have redshifted to wavelengths so long that no conceivable instrument could detect them. The cosmic microwave background itself will have faded beyond detectability, its photons stretched to wavelengths so long and its intensity diluted so thin that no instrument could distinguish it from silence. A civilization arising in Milkomeda at that distant epoch would inhabit a galaxy containing perhaps 1 trillion stars, surrounded by nothing. Their most powerful telescopes, pointed in any direction, would reveal only darkness. No other galaxies, no cosmic web, no filaments or clusters or walls, no background radiation from the Big Bang. Nothing that would suggest the universe ever contained anything beyond their own galactic borders. They would have no way of discovering that the universe is expanding, because there would be no distant objects against which to measure the expansion. They would have no way of inferring the Big Bang, because the evidence for it would have been carried beyond their horizon by the very expansion it set in motion. They would look out at a cosmos that appeared static, solitary, and eternal, a single galaxy floating in an infinite void, and they would have no reason to suspect that this was not how the universe had always been. They would develop their own cosmology based on the only data available to them, a single galaxy surrounded by infinite empty space, no expansion, no beginning, no other structures. Their physics might be brilliant, their mathematics might be flawless, but their cosmology would be wrong. Not because of any failure of intellect, but because the universe would have removed the evidence they needed to get the right answer. We know this because we can see what they will not be able to see. We live at the moment when the evidence is still accessible. We are the last generation of observers who will ever have the full picture, or at least as much of it as the current cosmic horizon allows. Every generation that comes after us, every civilization that arises in the deep future, will know less about the universe than we do now. The cosmos is not revealing itself to us. It revealed itself, briefly, and it is now in the process of taking that revelation back. This is not a thought experiment about some impossibly distant future. This is the confirmed trajectory of the cosmos we inhabit. The laws of physics, as we understand them, guarantee this outcome. Dark energy is measured. Cosmic acceleration is confirmed. The expansion rate is known. The math is not ambiguous. The universe is headed toward a state of ultimate isolation, and nothing in our current understanding of physics suggests a mechanism that could prevent it. We live in a privileged moment, a brief cosmological window during which the universe still wears its history on its sleeve. We can see the cosmic microwave background. We can map the large-scale structure of the cosmic web. We can observe galaxies at distances of billions of light years and reconstruct the story of cosmic evolution from the Big Bang to the present. We can look out at 2 trillion galaxies and know, at least in principle, that they exist. Future inhabitants of Milkomeda will have none of these advantages. The universe will have hidden its own past behind an expanding wall of darkness. The greatest story ever told, the story of how a hot, dense beginning gave rise to stars, galaxies, planets, and possibly life, will be erased from the observational record, not destroyed, not lost to decay, simply carried beyond the reach of any observer, no matter how sophisticated, no matter how determined, no matter how long they wait. There is something deeply unsettling about a universe that erases its own evidence, a cosmos that produces observers, and then, over time, removes the very data those observers need to understand where they came from. It is as though the universe grants a brief window of cosmic self-awareness and then slowly closes the shutters, leaving each surviving galaxy alone in a darkness that offers no clues about the grander reality beyond. The loss would be total, not just observational but conceptual. The very ideas that define modern cosmology, expansion, the Big Bang, the cosmic microwave background, the age and geometry of the universe, all of these depend on observations that will no longer be possible. A civilization in Milkomeda could be as intelligent as any that has ever existed, could develop physics and mathematics of extraordinary sophistication, and yet it would lack the raw data needed to discover the most fundamental truths about the cosmos it inhabits. It would be like a historian locked in a room with no documents, no artifacts, no records. The history happened, the evidence was real, but it has been removed, permanently, by the very processes that created the room in the first place. The universe does not merely isolate its inhabitants from one another, it isolates them from the truth. And the voids do not merely separate, they define. The character of the universe is not determined by the galaxies within it, but by the emptiness between them. A universe with 2 trillion galaxies packed into a volume where each one could see and reach its neighbours would be a fundamentally different cosmos from the one we inhabit. Ours is a universe where the dominant feature is absence, where 80% of the volume contains almost nothing, where the largest visible structures, galaxies spanning hundreds of thousands of light years, are still dwarfed by the voids between them by factors of hundreds or thousands, where even the most magnificent galaxy, containing 1 trillion suns, occupies a space so small compared to the surrounding emptiness that it amounts to a speck of light in an ocean of dark. This is the terrifying truth that lies beneath every measurement and every calculation. The universe is not merely big, it is built from isolation. The voids are not gaps in the structure, they are the structure. The galaxies are not the main feature of the cosmos. They are the rare, thin, luminous exceptions to a rule of overwhelming emptiness. The rule is the void, the exception is the light. And the exceptions are separated from one another by distances so vast, through environments so barren, across timescales so long, that the word separation barely begins to capture the reality. Think of it this way. Every galaxy in the universe is a campfire. Some are small, flickering things. Others are roaring bonfires throwing light across hundreds of thousands of light years. But between every campfire and every other campfire stretches a darkness so deep and so wide that no one sitting at any fire can see the glow of any other. The fires burn in absolute solitude. Each one heats its own small circle of space. Each one illuminates its own tiny sphere of matter, and beyond that sphere, in every direction, the darkness goes on forever. The campfires are real, the warmth is real, the light is real, but the darkness between them is so much vaster, so much older, so much more fundamental to the nature of the cosmos, that the fires begin to seem like accidents, brief, bright, improbable interruptions in a universe that is, at its core, made of dark. This is not nihilism, it is observation. The universe does not owe us connection, it does not owe us neighbours, it does not owe us a cosmos that feels warm or full or navigable. It simply is what it is, a vast, expanding, overwhelmingly empty structure in which matter occasionally organises itself into brief concentrations of complexity that call themselves galaxies. Those galaxies are real. The stars within them burn with genuine fury. The planets that orbit those stars host genuine chemistry. And on at least one of those planets, the chemistry became complicated enough to look upward and ask questions about what lies beyond. The fact that the answer is mostly darkness does not diminish the question, but it does reshape the meaning of the asking. Perhaps the most haunting aspect of this isolation is its silence. The void between galaxies does not roar or howl or whisper. It produces no sound, no vibration, no signal. It is the quietest environment in existence. A silence so absolute that it makes the vacuum of interstellar space seem noisy by comparison. At least within a galaxy, There are pulsars ticking, magnetars screaming, supernovae thundering across the electromagnetic spectrum. Between galaxies, there is only the faintest hiss of the cosmic microwave background, growing quieter by the epoch, fading toward a silence that will one day be complete. The void is not just empty of matter, it is empty of information. It is empty of story. It is the place where the narrative of the cosmos ends and the blankness begins. We sit at one of those campfires, the Milky Way, 400 billion stars burning in a spiral of light and gravity, planets orbiting in habitable zones, complex chemistry assembling itself into life on at least one world and possibly on billions, intelligence emerging, looking upward, building telescopes, mapping the cosmos, asking the oldest question, is anyone else out there? The answer, as far as intergalactic distance is concerned, is that it does not matter. Even if the answer is yes, even if every galaxy contains a civilization, even if the universe is saturated with life from one end of the observable volume to the other, the distances ensure that each civilization sits at its own campfire, warming its hands against a cold that extends in every direction without limit. The campfires cannot see each other. They cannot reach each other. They cannot confirm that the others exist. They burn alone, separated by the deepest and most permanent isolation the laws of physics can produce. 2 trillion galaxies, each one a world unto itself, each one containing enough stars and planets to make the question of cosmic companionship feel urgent and answerable. And between every pair of them, a void so vast, so empty, and so relentlessly expanding that the question becomes not whether someone is out there, but whether out there even means anything when the distances involved exceed the ability of light itself to bridge them in any meaningful time. The universe is full of galaxies. It is empty of connection, and that may be the most unsettling truth that astronomy, in all its centuries of looking upward, has ever had the precision to reveal. The distance between galaxies is not merely large, it is the defining feature of the cosmos. It is the architecture of reality. It is the silence between the notes in a symphony that plays across a stage too wide for any audience to hear more than its own small section. We are here. We are real. Our campfire burns, and the darkness around it stretches farther than we will ever be able to see, farther than we will ever be able to reach, farther than any signal we send will ever travel before the expanding void swallows it into silence. The galaxies are out there, trillions of them, each one as real and as full of possibility as our own, and every one of them is marooned, as we are marooned, on an island of light in an ocean of dark that has no far shore.